Well, welcome to week 7, and today we're going to be talking about agriculture as the intersection of where land use, water use, and energy all come together. Now, we haven't talked much about land use, and we're only going to hit that a little bit in today's lecture, but it shows again, the use of these three resources. And we know from the past from past lectures that agriculture has an enormous impact on our environment in water and energy use, and that's also the case with land. And we've seen before that energy and culture are formed around energy use, and this is no different for agriculture. The fundamental changes in energy use will change agriculture. And on a positive note, there are some innovative and sophisticated technologies that are being used on farms, both large and small, that will help us meet the demands of future of our population for food. So the overview of this presentation today, I'm going to talk about agricultural impact generally, the energy that's required for agriculture, the green revolution, energy that's embedded in food, just like we saw water embedded in food. We'll look at energy embedded, and then we'll look at sustainable food production, in particular some different forms of farming, and a little bit about the cycle of having grazers on the land and how that can lead to better soil and then better production and more food for the grazers. And then finally, two things where we have agriculture versus food production, the difference in not agriculture is for food production, and then also how we can combine agriculture and ecology to get better biodiversity and, in fact, look at that in the context of economic growth. So first, let's look at agriculture, the impact, and again, using the I-PAT relationship. We can see that agriculture has a big impact because it's the largest user of water in the United States, and the United States is an industrialized country, so less of the economy relies on agriculture. For countries that have high irrigation demands and low industrialization, this could be the overwhelming use of water. In energy, agriculture uses 17% of all the commercial energy in the United States, and that's for the energy used in traction on farms, moving things around and plowing, the energy that goes into making petrochemicals like fertilizers and herbicides and insecticides, the energy it takes to process the food, and the energy it takes to distribute the food across to the market. And finally, agriculture has a huge impact on CO2 emissions. You can see it's 17% of all commercial energy, and it's 20% of CO2 emissions. Those numbers sort of line up, but because of the particular nature of farming with cows and rice paddies and soil chemistry going on, it's 55% of the methane, and methane is 26 times as strong as a greenhouse gas as CO2. So this is, when we talk about greenhouse gas emission controls, methane is a major target. So when we talk about greenhouse gas taxes, it's not just CO2, it's methane, and this would really hit farms hard. The other thing I want to mention here is we've talked about population affluence and technology. And for agriculture, the impact of technology is very asymmetric, especially when you look in an area like Portland. You can have a really high-functioning piece of land for agriculture, growing crops, growing healthy food for people, but yet there's just not that much technology devoted to it that would maintain that state. Within just months, you can come in and construct a building, and that building could be one of the worst buildings you've ever seen and could be there for 20 years. So there's some aspects of technology that sort of ratchet the environment in one way, and agriculture really doesn't get to take advantage of that too much, the individual plots. You can have an excellent pasture and just have it paved over for some sort of storage company with a big parking lot and a few storage bins. It's amazing that there's really, in most places around the country, very little protection for agriculture. Now, in Oregon, we have very strict land use planning and land use laws, and that actually protects agriculture from these sorts of abuses. But even then, once it's lost, it's really hard to go back, to turn a road back into a farm. It's easy to turn a farm into a road, but vice versa is very difficult. So this is one aspect of technology that we mentioned a little bit before. Once a decision is made and you put in green infrastructure, but then it's hard to reverse. But it's important to take into account for agriculture. This is a big challenge for agriculture. So again, we saw that it's a major portion of the water budget, a substantial portion of the global energy budget. But let's look at the land that's in agricultural production. And of the total global land use in billions of acres, cropland accounts for 11% and pastures for 27%. So combined, they account for 38%. And the cropland would be, irrigated or row crops, fertile soil that can be, produces vegetables and fruits. Pasture, you would run stock on it and then either harvest that for meat or use that for milk production. And it's usually a lower grade soils. Non-arable, this 21% of the earth is non-arable. This would include deserts, mountaintops, rocky areas, things like that where you just can't grow anything. Many urban areas have been put over farmland because cities were formed and started in valleys on river beds, on river systems, very fertile land. It's been created into urban areas. And then forests is sort of a mix. We'd have to do a different sort of accounting to find out, because there's national forests, like just in the United States, there's national forests, there's private forests, and then there's plantation forests that look a lot more like agriculture than they do like a natural forest. And another thing to consider is that around the world, 40% of the agricultural land is seriously degraded. That means that it's way below its potential for producing crops because of abuses abuses to the soil, overwatering, over-fertilization, too much plowing, wind erosion, those sorts of things. Those all lead to degraded farmland. So the economics of land use and farming is also interesting in that a third of the population works in food production. Well, since about a third of the population in the world is subsistence, rural, or urban poor, this they might have very close ties to this sort of food production. It's not really a major employer across the industrialized world, but less than 5% of the global GDP is it covers agriculture, which means only about a 20th of the global economic activity is in agriculture. So any increase in this number here, the 5% global aggregate GDP, would mean food is getting a lot more expensive, and that increase would be passed on to people. So it's not necessarily we want that number to go up, but it just shows what a small part of the overall economy it is for an essential commodity, commodity, which is producing food. Now we can treat the agriculture like, what's the role of energy in agriculture? And before we saw how energy was related to different agricultural processes, such as and food gathering process, such as this was from the lecture on energy and society. We had hunter and gatherers, just what your personal metabolism is, going around collecting your food. That's about 2,500 kilocalories per day. And moving up through subsistence agriculture, having animals, small amount of water power maybe, and then commercial agriculture where you get more food than you can need, and goes to has to be collected and stored someplace, goes to market. All of these are ways that energy impacted the role of the choices that society had for how they organized commerce in society. But I'd like to present another version of how energy can affect agriculture by looking at the amount of energy that goes into machine capital, human labor, energy such as for traction and distribution, and then chemical costs, and those chemical costs are another form of petrochemical, and then land. So these types of effort and capital. So for low technology farming, which is, think about this as sort of subsistence level farming, or actually farming for a small local market, these farms are smaller, they're less productive, they require a lot of human labor, but they really don't require very much traction, other energy, or chemical costs, and again, they're small, so they don't require much land. So that's low-tech farming, and this could either be something like subsistence farming, or in the United States you might see this as community-supported agriculture. A lot of those are organic, so they really don't use a lot of chemicals. Then there's a category called intensive agriculture, and for this, think of rice paddies. Rice paddies have high human labor, everything's planted by hand. There may be a lot of petrochemicals being used for fertilizers and herbicides in order to get high yields out of this. They might not use very much traction, especially rice paddies. They use small little devices that look like a rototiller that they use in these small plots, small land use, but very high productivity. The other place you see this is in sort of high value crops in the United States that are farmed on a very small area and heavily cultivated by humans, such as small vineyards, some other agriculture such as that. And then the other category here is industrial agriculture, where there's low human labor because a lot of it's mechanized. And because a lot of it is mechanized, you have a lot of energy going into traction for plowing, for moving stuff around, for delivery. And then you have fertilizer costs, which is again another form of petrochemicals. So the nitrogen fertilizers are derived from using natural gas and creating nitrogen fertilizer from that energy and from that source. And then you have the use of machinery. This could be for processing and transport. And then these industrial agriculture can grow on a lower grade of soil, but they need a lot of area and they use fertilizers and fuels. So this industrial agriculture is very common. When you think of, say, irrigated corn, this is a good example of this industrial agriculture. Okay, now there's another taxonomy that I want to use. It comes from Michael Pollan book where he talks about industrial, which is just like what I talked about up here. Industrial organic, where you do the same sort of things. There's low labor costs, but there's a lot of machinery used, but they just don't use fertilizers and herbicides. They would use recycling and composting instead of that. So again, it's another form of another way they use energy. And again, they can build the soil. This is one of the big things about organic farms, is the soil actually becomes more valuable as it's farmed rather than depleting it. And then the final type is this artisan, a very high degree of skill, a high degree of information capital, some nice examples of technology, and we're going to see this when we talk about polyface farms here in a little bit. Okay, now I want to talk about how this industrial agriculture came about, and one of the ways it came about was through the Green Revolution. And this is not the Green Movement, this isn't politics or the Sierra Club, it's the Green Revolution, where it brought together sophisticated plant genetics in labs all around the world, not genetically modified, just the old school, growing plants, selecting the ones that did best, very cutting edge genetics, but not moving genes around. And what they're able to do with that was create higher yields of grain and rice. And these higher yields mean they had usually less stalk and more grain. So the shorter, sturdier stalk was actually able to hold more grain at the end. And that made it hardier for mechanized harvesting, but it also made it shorter and more susceptible to being overgrown by weeds. This was combined with the availability of irrigation, again through the industrialization of agriculture, followed sort of the electrification of the rural West in the United States, where there was dams and reservoirs and electrical power to move water around. All of those were allowed this sort of water to be moved around and used for irrigation, either pumped out of the ground, the aquifer, or to be moved from reservoirs over to the farms. And finally, the use of petrochemicals of all sorts to make fertilizers, nitrogen and phosphorus, require to either create the nitrogen fertilizer or to mine the phosphorus and transport it. They used petrochemicals to create herbicides and pesticides, and these were the result of munitions and nerve gases and things they had during World War II. They figured out that as they decommissioned those, they could turn them into herbicides and pesticides, and then that practice continued and that part of the industry grew. And also traction, by that I mean all forms of mechanical movement that depend on fossil fuels. And a real large amount of the sector depends on diesel. So these were brought together, and the people that did this, the benefits from this were meeting food demands for developing countries. And when I was a kid in the 60s, that meant meeting the food demand in India, for example. Large areas of that country had incredible increases in their production of food, and that provided higher food security, which allowed that India to develop into the largest democracy on the planet. And then for other areas, there was excess food, which allowed for trade and providing food across the world when there was food stress, shipping that all around the world. So it was a different sort of foreign policy based on food availability and relief efforts. The disadvantages were that as they bred these stalks of plants, there were many fewer varieties of plants being used. Instead of every farm having a little different variety of corn and grain, they were very standardized forms of these grains, and that depleted the natural range of crops and made them much more susceptible to insects and blights and weather conditions. And because of that, people became dependent on buying the next year's seed from the same store. There's a dependence on irrigation, which led to more severe impact when there was drought. Instead of being a range of plants that could maybe weather where the crop some part of it might fail, when you had a drought and they were very dependent on the water, then the whole crop would fail. And finally, this dependence on energy subsidies, both in pumping water, petrochemicals, transport to market, all of those things were created by this more industrialization of the farm system. There's a couple indirect effects of these processes that you might not have seen might not have predicted right away. One was overall water consumption as they grew plants that needed more water, that is, were inefficient at their use in water and growth, moving that agriculture further and further away from population centers and using more and more irrigation. The water consumption just skyrocketed. And another effect which is close to my research area, which is this lake eutrophication, where you get a lot of algae growing in the lake. Because there was excess water and excess fertilizer used, it ran off into the streams and rivers, and then you had a lot of algal growth, and that's one of the main sources of degradation of the water resources in the United States. All right. One of the other aspects we can look about energy, the role of energy in agriculture, is how much energy is embedded in food. Just like we looked at the water that's embedded in food, we can do the same sort of accounting, look for energy. And so a couple of things, though. It's not the food that really is that much energy in it, but it's embedded in the full life cycle. So we're not looking at how much energy is just in the nutrition of the food, but how much it took to create that. And then also we can see that recently people consume a lot more goods, bigger cars, more gasoline, but they consume about the same amount of food. And that choice of what food they eat may require more or less water or more or less energy. So let's just look at a few examples of the energy embedded in food. And in this case, let's look at a couple examples. It takes 68 kilocalories of fossil fuel to make 1 kilocalorie worth of pork. That means it takes 68 times as much energy as you get out of it biochemically, just for your own nutrition. That's the 1 kilocalorie worth of pork. It takes 68 kilocalories of fossil fuel. That's in traction, and in petrochemicals, and in shipping it and processing it, all that to make just 1 kilocalorie worth of pork. That's not counting the solar energy that went in or the value of the land. It's just how much fossil fuel. And beef is a little bit better with 35 kilocalories worth of fossil fuel to make 1 kilocalorie worth of beef. And again, this is related to the water, how much water was embedded in beef. It was like many gallons per kilogram of beef because of all the process, of all the growing the product, growing the food for the beef, and and then washing it, and all those sorts of processes. So just having studying this sort of life cycle of energy involved in food production can result in a 5-fold difference across different foods. So and then animal products range about 4-fold. So the particular energy that is embedded in food is highly related to where you got that food and how it was processed and how it's delivered. So in a Swedish study, it's referenced down here, to eat local clams was about 10 times more energy than if you you got your same protein and nutrition from a local cow source. So again, you have to look at the very specifics, just like we saw with diapers, where the water came from, where the cotton was grown, how it was handled. This analyzing the very specifics of what food source you ate is hard to generalize across all of these food types. Okay, one final comment is that EcoTrust, which is a local, which is in Portland, and one of their main ways they study the world is through this idea of the Salmon Nation, which is Oregon, Washington, Vancouver, BC, and Alaska. These salmon that were related bioregionally through the salmon. So they're very interested in salmon, but they found out that fresh salmon costs 57 times more in CO2 emission than frozen. And that's because in order to get fresh salmon, you have to fly it in from these remote fisheries, whereas frozen salmon can be stored on a ship and just brought through surface transport, and it costs a lot less energy and therefore a lot less CO2. So this is sort of a surprising result, and it shows going out to dinner and having a fresh caught salmon that was flown in the day before has a big CO2 impact on the planet. All right, I'm going to take a break here, and we're going to come back in part 2 and look at sustainable food production, including these artisan farms, and then we're going to compare some aspects of agriculture to just the food production part, and then see some examples of where agriculture and ecology can work well together.